everyone. My name is Kanchan Dikshit and today I am going to discuss about the Booth algorithm for multiplication. So first we all know that what is multiplication, how is being multiplied within the computer. So this is the multiplication process that is being done by ALU unit. So for any kind of operation being done within the computer is with the help of arithmetic logic unit. So multiplication for multiplication, there is also the responsibility is done by ALU unit. So there is also a simple multiplication algorithm, but both algorithm makes it different because it is using 2's complement when it finds the combination of 1 0. Right. So this is how this we can say the both algorithm is working for multiplication in an efficient way. So we are using it and it is so now I can say this is the flowchart for both algorithm. So let's start. So I'm going to explain the both algorithm multiplication flowchart. Right. So we are going to multiply for two integers. The first integer will be entered inside m variable that is storing multiplicand, and q is treated as multiplier. Now we are taking one additional bit that is q minus 1. What is this q minus 1? Suppose I am taking that q is somehow 0000. So this is the least significant bit and treated as q naught. But I need to take one additional bit that is q minus 1. And on the basis of this combination, if it is 00011011, on these particular combinations, the both algorithm works. So I can say if this q naught, q minus 1 is 00, then only arithmetic shift right will be there. For okay, and for 1 1 also there will be arithmetic shift right. But if this combination becomes 01, then we need to add m as in the accumulator, right? So for that, first we need to initialize the accumulator with 0, and the number of bits will be same as m. Right now the number of bits will be how many number of bits are there. Okay, so this will be treated as the counter for the number of cycles this particular algorithm is going to work. And every time this n will be decremented by 1. If n becomes 0, the result you can find in the AQ. Otherwise, you need to work for the next counter bit. Right. So this is the flow chart. Now we'll understand it with the help of example. Right. Now, what are the facts about both the multiplication algorithm? So this is the multiplication algorithm. It multiplies two signed binary numbers with the help of 2's complement. Now, it is being invented by Andrew Donald Booth in 1950, and the name of the Booth algorithm is because of them only. Now, the advantages. So advantages are this is faster than traditional multiplication. It is efficient for signed numbers. It is lower. It is having lower hardware requirement, and it is widely used in hardware. Now, what are the disadvantages? It is complex to understand. It is limited applicability. Limited applicability says that it can be applied up to a limited number of bits. If you can say I need to multiply like for 10-bit integer, so it can't work. I cannot say it can't work, but it will be complex for the bigger numbers, right? So it is all about this. Now higher latency, until we can complete the cycle for one counter bit, it cannot be completed for the next counter bit. Now higher power consumption, so it can take the higher power also. What are the possible cases? So with the help of this, we can multiply positive number with the positive number. We can multiply positive number with negative number also, right? And it can multiply negative number with negative number. So for this, I guess I need to make two or more videos to implement this with the help of science. Now this is the first question. We are going to start with plus sign with plus sign multiplication. Okay, so let's start. So I need to take m and I'll give it plus 7 and I'll have q as multiplier, m as multiplicand. So first integer will become multiplicand and the second integer will become q, that will be multiplier. Okay, so both are the numbers are positive, so I will take the binary equivalent of these numbers. So what is the binary equivalent of m? That is 7 0 1 1 1, right? With 2, and it is like 0 1 1. Okay, so somehow we need to take both of the numbers as positive. So I'll take this additional bit to signify that this is a positive number. There is no addition for this bit. There is no reason to add this bit. There is only the reason if I'll take it as 1 1 1. So somehow it can be treated as negative number. So I don't want it. I just want to treat this 7 as positive number. So I'll take one additional bit that will signify its sign. So same will be applicable here also. Now here I'm taking two zeros. So first zero will be, first zero will be used just to equalize the number of bits in multiplicand and multiplier. Okay, so this zero will be for the equalizing the number of bits, and this zero will signify the number as positive. Clear? Now what we are doing there we are going to apply two operation. One will be a plus m and other will be a minus m. Okay, so this will be minus. So for a minus 1, what we are doing in Booth multiplication algorithm, that this minus m will be treated as the 2's complement of m. So 2's complement will be added into this accumulator value, and that will give you a minus 1. So let me show you a plus minus m. This minus m is 2's complement. Okay, so what we are doing, we are going to compute this minus m also. So this minus 7. So how to compute it? So we are taking minus plus 7, that is equal to 0 1 1 1. Okay, now the first complement is 1 0 0 0. Okay, and second complement says that I need to add plus 1 here. So 1 0 0 1. This will be the value of minus m or minus 7 here. Clear? Now let us take the example. So what we are doing here, we need to initialize the accumulator with the number of bits in multiplicand. Now 0 0 0 0. Q will be 3. So the binary equivalent is 0 0 1 1. Q minus 1 will be initialized with the help of 0. N will be 4. That means the number of bits in the multiplicand says that it will be equal to n. Now what operation to be performed? We need to find out the Q naught and Q minus 1 combination to figure out what operation will be performed. So there are total two operations, A plus M, A minus M, and only ASR. Okay, so plus M says that the value that is 0, 1, 1, 1 will be added. For minus M, 1, 0, 0, 1 will be added. And ASR says that if we need to perform ASR for this value, that is 1, 0, 0, 1, so it is arithmetic shift right. So every value will be shifted to right for one place only. Okay, so this will be 0 and this 1 will be discarded. Okay, now what is about this MSB? So MSB will be copied or it will remain same. So the ASR, after the ASR, the value will become 1100. Okay, so now for 1-0 combination, we can find out that the operation will be performed, that is in accumulator A minus M will be computed. So A is 0, 0, 0, 0, minus M is 1, 0, 0, 1. So 1, 0, 0, 1 will be there in accumulator now. And the Q will remain same. Q minus 1 remains same and N is same. Now, after this A minus M operation, we need to apply arithmetic shift right. Okay. So after this, the value becomes, okay. So ASR will be applicable to accumulator Q and Q minus 1. Okay. So now this 0 will be discarded. This 1 will be at the place of Q minus 1, or Q naught will be at place of Q minus 1. Now Q naught will be same because the next bit is also same. Now I am performing Q minus M, sorry, arithmetic shift right. This 0 will become, this 1 will become 0. Then this 0 will be placed here. 1 will be placed at the place of 0. And 1 will be copied as MSB also. So this is the final result after ASR. Clear? Now we need to see that after ASR, the counter will be decreased by 1. Okay. Now we are performing it for n is equals to 3. Now the value is 1, 1 for Q naught and Q minus 1. Now for 1, 1, we need to perform only ASR. Right? So we'll perform ASR 1. This 1 will be discarded. Clear? Now this 0 will be at the place of 1. This 0 will be at the place of 0. This 1 will be at the place of 0. And this 0 will be at the place of 1. Clear? Now this 0 will be at the place of 0. The 1 will be at the place of 0. The 1 will be at the place of 1 and MSP will be copied. Okay. So just the counter will be decreased by 1. Okay. So this will become 2 now. The value will be same. So we need to copy here. Now again we need to check the combination of Q naught and Q minus 1, that is 0, 1. So for 0, 1 we need to perform A plus M. Okay. A plus M. A plus M says that 1110 is the current value in accumulator and plus M value is 0111. Now this is 1, this is 0, this is 1 and this is 0 and this is 1, that will be discarded. Clear? So the value now in accumulator, that will be 0101. The value of Q will remain same that is 0, 1, 0, 0. The q minus 1 will be also same. Now the second operation is ASR, that is being performed after each operation. Now after ASR, this 1 will be discarded. The 0 will be at one place. This will be 0. This will be 1. This will be 0. It will become 1. Now it will be 0. This will be 1. This will be 0 and this will be copied also. 0 will be copied also. So now the value in accumulator is 0, 0, 1, 0 and in Q is 1, 0, 1, 0 and in Q minus 1 it is 0 and the counter will be decreased by 1. So it will be 0, 1. Now we need to check the combination, that is 0, 1. So for 0, 1 we are going to perform again sorry. Okay. So after this, the combination becomes 0, 0 and now 0, 0, 0 says that the only ASR will take place. Clear? So this 0 will be discarded. 0 will be at the place of 0. 1 will be at the place of 1. 0 will be at the place of 1. 1 will be at the place of 0. This 0 will be at the place of 1. And this 1 will be at the place of 0. This 0 will be at the place of 1. And this 0 will be at the place of 0. And this 0 will be copied. Right? And the counter becomes 0 now. So as the counter becomes 0 or n is equals to 0, we need to check the result in accumulator and Q. So this is the result, guys. So we can find out that the result is 0, 0, 0, 1, 0, 1, 0, 1. Okay, so these 3 0 we need to include in the result. Okay, so this 0 indicates, the MSB indicates that the result is positive. Okay, now we need to find out the decimal equivalent of 10101. So we can say 0, 2 to the power 0, sorry, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. That means 16, 4 and 1. That will become 21. And somehow our result is also 21. So this is all about Booth algorithm. These are the applications of Booth algorithm. There is some application that is we can use this Booth algorithm in chips and computer processors, in digital signal processing, in hardware accelerators, in cryptography, in high performance computing, in implanted frameworks, in network parcel handling, in advanced channel and balancers. And for reference, guys, I have used Morris Menu here. That is the book for computer system architecture. Okay, so thank you.